lecture we have been discussing about the lambda based design rule that is scalable. That means we can change the technology without changing the design. So different lambda based design rules exist here for different parts or different parts of the say transistor. So like here in this diagram we can in detail see that contact. Okay, if we have to make a contact between say one layer to other layer, we can take the help of via. Okay, this vias. Okay, and the minimum size of these are going to be 2 lambda by 2 lambda. Okay, so these numbers which we see in this and these are in terms of lambda. Okay, it means 2 lambda plus 2 lambda like this. So 1 unit means 1 lambda. Okay, so the separation and the colors. Okay, these represent different layers. Like green is shown by active layer here. Active layer is shown by green color. Polysilicon, we use 2 layers of polysilicon, and poly 1 is of red color, poly 2 is of this color, metal 1, metal 2. Okay, so these are just different color codes which are usually used. So we can see that here, let us look at the first case here. What we mean by this here? In the first case, we are having this overlap of green and blue regions. Okay, so blue is the metal one, and the green one is the active region, and black here which is there. And this is contact, metal contact through B. Okay, so we are contacting this metal one with active region. It means through this, and the different sides of these regions should be like this here. So nowadays actually this comes into physical design. Okay, this is something a part of physical design in which we can design the layout. Okay, so there is also dedicated softwares which can generate for say digital circuits. Mostly they can map directly transistors into a particular layout for a particular technology. Okay, so technology node is okay different. Like we talk about say 90 nanometer technology node, 130 nanometer, and so on, or 65 nanometer. So these are technology nodes here. Whereas the uh, different fabrication labs, okay, they do have their own specifications of the transistors depending on their available capabilities. So they design a particular library of these transistors which they call as PDK. Okay, so PDKs consist details of the particular technology. Okay, at a particular technology node from a particular fabrication lab. Like for SCL, we have a PDK for 180 nanometer technology node, or 150 nanometer technology node, and so on. Okay, separate PDKs will be there. So we can use these PDKs directly and map the our design, okay, the digital design onto that, and that will take care about this. But what happens sometimes that uh, the routing could be a problem. Suppose one tries to put these this into using the mapping, okay, using these particular technology nodes, then what may happen that it may occupy a larger area uh, because of the different connections present and unorganized, say, placement of these transistors here and there. So one can also do optimizations later on uh, and try to compact the size. Okay, so those are the things here which can be done, but here it is just showing here that what are the different rules which must be followed. This becomes important to know when we are doing the ASIC design from scratch. Okay, so say in analog design, we have to specify each and everything. Okay, even transistor, how, what is the size of the transistor, how we can put, how we put. So all these things are done manually. Okay, so in that case, mostly the knowledge of this layout design rules, okay, and that becomes important. Okay, so just here, this here it shows how um, the well and uh, this select, okay, well contact, these needs to be separated from each other, and so these just gives the minimum size and my minimum separations from each other. And if there is any violation of rule, okay, then there is something called as design rule check that can be done to find out where these rules are getting violated. Once our design passes all these checks, then we can generate our GDS2, okay, GDS2, which can be sent to the fabrication lab for final tape out, okay, chip fabrication, that is also called as tape out. So different layout rules are here. So if we look at an state of the art example of a 37 nanometer, okay, so this is for 19 nanometer technology node here, 0.09 micrometer from TI Texas Instruments. Okay, so this is a transistor from Texas Instruments having 19 nanometer technology node. So in this here, 19 nanometer doesn't mean that uh, the physical things will be 19 nanometer here. So a channel length is of 37 nanometer, as we can see here. This is actually the XRD image, okay, which has been generated. Different regions also we can see here in reality how they look like. So here something like these structures we can see here. These thick regions may be of oxide here, and in here the main region is not fully oxide here. Okay, here on one side here it may be source, on other side it may be drain here, and in the middle it is channel here. Okay, 37 nanometer. So physical thickness of uh, uh, may be different as represented by this technology node here. So A CMOS inverter layout is shown here. We will be discussing in details of these inverters later on. So in an inverter, mostly we have a PMOS and NMOS here, gate, VDD, and ground. Okay, like this. And there we have an output here from the common drain here. So a typical layout is shown over here of this full CMOS inverter, how it looks like on the silicon. So one can identify the different regions here. So this is here NMOS, below one, above one is the PMOS. PMOS is housed in N bell here, and substrate is of the P type, and the substrate, the NMOS is situated. And this is source and drain here, source and drain here. Okay. Oh, sorry. This is actually polysilicon. Sorry, this is polysilicon. Just I am highlighting here. This is polysilicon, and the input is given here. This is metal here, white portion, and here this metal layer and this polysilicon. These are connected through a via here with the minimum size contact over here. So source is on this side and drain is this side, and source is here on this side and drain is this side. Okay, this is active region. Here it is active region. So here we see that whenever there is a overlap of here active region here and polysilicon, there is the formation of this transistor. Okay, with source and drain on the other side. Drains on the other hand, both are connected together, and output is taken here. So N bell is connected with highest potential, as happens in the PMOS. Okay, source is a source and this well. Okay, so this is something like this here, that we connect this substrate. Okay, that is here N bell for the PMOS with source here. They are connected to the VDD. Similarly, for the NMOS, this source and substrate, these are connected to this ground. Okay, this is something to avoid the short channel effect. Okay, one short channel effect called as body bias effect. Okay, so body, to avoid this body bias effect, we do this. These are also discussed about this. So different views of the CMOS inverter are shown over here. One can try to understand here that this is just color coded CMOS inverter, and if we say cut from here and see from the front side, then this kind of all the regions may be seen here. Okay, so field oxides are used to isolate the different devices on this, on the same substrate here. Okay, so this drain of the NMOS and PMOS are connected together to take the output here. The gate is here, this red color, This is gate. This is also gate. The transistor. Here, source and substrate are connected together to provide the body bias effect here. Similarly, for the PMOS, the source, this N bell and the source, okay, they are connected to the BDD. So these are connected to the BDD. These are connected to the ground here. Okay, so this kind of cross-section views can be seen here. So different layouts may be there. Okay, we may stop here discussing about the layouts because you may not be able to appreciate this right now because you might not have seen all these things. Okay, so different layouts are possible here. Sometimes we need to have a very large, means wide transistor. So these are different ways how we can actually do this uh, layout design so that we have the maximum bits of the transistor. Okay, so let us hope that we will sometimes again review this layout. Okay, after doing other things. Now let us come back and refresh a little bit about this MOS transistor concepts, and then we will start discussing about the our first device, that is the inverter. Okay, in detail from the next lecture. So today we would just have a MOS transistor review. So MOS transistor already we have seen in the last few lectures that how it looks like really. So we can identify that this is nothing but NMOS transistor. Why it is NMOS? Because we can see N plus source and drain, and which is on the P type substrate here. So this is NMOS enhancement type of transistor. Okay. Enhancement type because there is already no channel present, but if we apply some suitable gate voltage here, then channel may be created here which will connect this source and drain together, and if we apply some voltage difference across this drain and source with the help of a BDS, then the current may start flowing. Okay, so if we apply this kind of BDS between the source and drain, then we can see that it will establish an external electric field which will be orienting from drain to the source side. Okay, this is a drain, this is source. So the electrons will get accelerated in the opposite direction to the electric field. So electrons, we will see that they are going to accelerate towards this electrons. Okay, from source to the drain side. So electrons flow from source to drain side, but the current will be flowing from drain to source side. Okay, so that's what we see here from here. So depending on the gate voltage here. Okay, so what is the amount of gate voltage, the inversion labels may change, and so the current may change and the transistor will start working in different regions. So here it shows the cross-sectional view of this same transistor here. A, on the P substrate, we have N plus source and drain here. Gate, which was seen generally, that has a width and a length. Okay, so length may be almost equal to that of the channel length. Okay, so this is what the channel is. The channel is the region between the source and drain. Okay, so sometimes this kind of situation may have like here, that a part of source and drain is coming under the gate. It looks like sometimes there may be the cases in which the source and drain may be away from this gate region. Okay, so depending on these, what type of uh, excuse me, what type of confusion we do have, we call it as overlap or underlap. Okay, so when a part of gate and source or drain overlap, then that is called overlap. Overlapping. Okay, or if they are a part away from each other a little bit, then that is called underlap. So we may have underlap transistors or overlap transistors like this. Whatever is the case, only the difference may be little bit in the threshold voltage and other things. Okay, so that is actually from the device part. One can also see these thick regions. These are the field oxides. Okay, so field oxide just isolate the only the active region. So the region which is closer to the surface. Okay, this region is called as active region, and this is the active region through which the current flows. Okay, that is the most important part. The current doesn't flow through this bulk. Okay, body side. Okay, so just some remarks about how we form this N region and P region, that is understood. So let us look at how we can look on this NMOS transistor. Okay, so we can understand the working of transistor using something called a switch model. Okay, so what does this switch model say? That when gate is off, okay, gate is open, then there is no current, and when there is a gate closed, we have this transistor just work like uh, an element of an equivalent resistance equal to R on. And current may pass through it. So the condition that gate is open is that when VGS is less or equal to less than VT. Okay, so VT is the threshold voltage. So a threshold, something called as threshold voltage, is required. Okay, this is already known to us. Just we are reviewing the concept here. Threshold voltage VTH. Okay, or BT here, which is written, is the minimum voltage required to be applied at gate to make or to induce this channel. Okay, so once the channel is there, then there could there could be a flow of current between source and drain. Okay. So BGS, the gate to source voltage, actually source actually B uh, take the source as reference. Okay, so source is taken as reference, and all other voltages like gate voltage or drain voltage, that is measured with respect to the source voltage. Okay, so we rewrite BGS or BDS in this way. So in this here, all the potentials are measured with respect to source. It means source is reference. Okay, source is reference and its potential is assumed to be 0 for n mass. Here mod is written so that this particular equation is equally valid for the p mass as well as n mass, both. So when our BGS is greater than BT, greater or equal to BT, then this will be on, and current may start flow if we apply a BDS. So similar thing is valid for, excuse me, hello, now कौन सा? अच्छा हाँ, दे दीजिए हाँ। वहाँ पता कर लीजिए कौन ले रहा है उसको। हाँ, मैं अभी आइडिया नहीं है कौन ले रहा अभी। Okay, so here for the P mass, it is BGS should be greater than BDD minus BT here. It is because this source is at BDD in the P mass, and we need to apply a gate voltage which is uh, which actually is greater than this value BDD minus BT. So for P mass, the BT is negative. Okay. So for this region, we have to ensure this. So if we want to make this transistor to off, then we have to ensure this, that BGS is greater than BDD minus BT, and if we have a BGS less than BDD minus BT, then this becomes on, and again we will see an equivalent resistance R on to be given in the on state of the transistor. So let us look at what we mean by threshold voltage here. So threshold voltage, as already understood here, that when we apply a gate voltage, that means a potential at gate with respect to source, that we talk in terms of BGS now, and this substrate, as we can see, and the source both are ground, at ground potential, at ground potential here. Okay, so if we apply a gate voltage, then depend here we have this n mass here. So what happens, the electrons starts appearing here. In the starting, what happens, that there is no electron. Okay, if we apply a gate voltage, then and we will see some negative ions to be present here. We apply a positive gate voltage. Okay, so negative ions means what? It is p substrate. Okay, this was fully p substrate everywhere. This was p type here. Under this is p type here. So electrons are attracted from the substrate side as we apply gate voltage, and these electrons go and are being accepted by the acceptor atoms here, because this is p substrate means it is doped by acceptor atoms. So, and in the neighborhood of this gate here, we have the acceptor atoms which accept the electrons, because electrons are being attracted towards this side here. Okay, the electrons cannot cross this region because in the middle here we have the oxide here. Okay, I just didn't discuss this, but this is silicon dioxide insulator which separates this gate with the channel region. Okay, or substrate region. So these electrons just stuck here at the interface of silicon dioxide and silicon. So this is what this interface line is here, silicon dioxide silicon interface. So initially, as we increase the gate voltage, then these electrons are just accepted by these acceptor atoms. They become ionized. They are having negative charges now. So equivalent charge is induced on the other side. Okay, as we put some charge by applying a positive gate voltage on the gate, equivalent charge starts building up on the other side because of the capacitive effect. Okay, we see here a capacitive effect to start working, because on the other side, on the both sides of the silicon dioxide, we have the conductive regions. On the one side it is polysilicon. Okay, on the other side it is silicon, but that is doped, so that has some conductivity. So because of this, it gives rise to a capacity effect. Okay, so this is due to this capacity effect only happening. So as we increase gate voltage more and more carriers are attracted from substrate towards this interface, and this acceptor ions region that keeps on growing like this here. Okay, so this in this region by now there is no charge carriers which can contribute to the current. Okay, this is called as depletion region. As you can see here, it is written as depletion region. What is depletion region? In the depletion region, there is no mobile charge carriers. Okay, uh, which can contribute to the current, but there is negative charge due to the acceptor ions. So these are acceptor ions here, which are there present. Okay, so every here also the acceptor ions are here, not being shown here, but acceptor ions are here also. So here in these regions from where this etc. is coming, because of formation of Pn junction. On the one side, one can see it is P type substrate, and on the other side it is N plus drain or N plus source region. Okay, so we have a formation of Pn junction here. Okay, so Pn junction is found over here. So Pn junction is found over here. But under the gate there is the capacitive effect which exists here and is responsible for this action here, to because of which this depletion region appears. If one keeps on increasing this positive gate voltage, then uh, after a time what happens that electrons don't get acceptor atoms here. There is no more etc. atoms with which they can combine, but they start building up here, okay, in the form of a thin layer. So a thin layer is there present. So a thin layer is present here. So this is the thin layer of the electrons. That is what we call as channel. This is n channel which is formed now. And now if we have in this situation, what we can see that drain and source, okay, both are grounded. So we will see no current between drain and source to flow because drain and source are at the same potential. So the value of BGS where strong inversion occurs is called the threshold voltage BT. Okay, so to have more understanding of this, one can follow some device physics uh, book and see what we mean by strong inversion. So there are normally three inversion regions which are defined. Inversion regions. So first is called as weak inversion. Second is and third one is written here strong inversion. Between weak and strong, we also define something called as moderate inversion region. Okay, so in the moderate inversion region, neither this is we can say very weak, okay, or not strong, but it is in between. So okay, so after when the channel is strongly inverted, then in that case we have very huge amount of the channel charge. Okay, so if we apply gate voltage more beyond this in the strong inversion, then the channel charge, okay, this channel charge, that is electron, that almost increases linearly. Okay, so channel charge increases linearly, that is called as a strong inversion. And in weak inversion, the this is exponentially increasing, but the amount of charge is very low. Okay, so the comparison is done with the amount of say uh, carriers present in the substrate. So this is a p substrate. Okay, so in the p substrate, holes are the carriers which are present. Okay, so in equilibrium condition, the concentration of holes, whatever it comes here, if we are having the electrons in the channel region to be of the same order as the holes in the substrate, then we say that it is inverted. Okay, the channel has been created. So strong inversion is this one, and we call this corresponding value of the gate voltage for which this happens as threshold voltage. This is what the concept is behind this. So the main part of a MOS transistor, as we can see, it is having the source drain, of course, a substrate is there, apart from the channel part is there, and then this gate part is here. So main part of this seems to be this one where most of the action happens here. This region is called as metal oxide semiconductor stack. Okay, so metal like behavior is given by this polysilicon here, oxide is here, and this is silicon. So mass structure. Okay, so that what is the heart of this MOSFETs, and it is shown over here. So we have metal gate, metal like gate, or metal gate itself. Okay, so heavily doped silicon that we call as polysilicon that also is having metal like characteristic. So, and this is here oxide, and this is semiconductor. Something okay, just the those things we just we have qualitatively uh, discussed here, that is enumerated over here in this slide. When Vg is less than threshold voltage, then we have the holes to be here at the silicon dioxide silicon interface. Okay, this is silicon dioxide silicon interface. This is silicon dioxide white region, and this is here gate region, and this is here silicon, p-type silicon. Okay, so if gate voltage is negative, that is shown by negative charge here, then we have on the other side, due to the capacitive coupling, a positive charge equivalent. Okay, so p-type substrate was already there, some holes were there. Now a little more holes come to compensate for the change on the other side in terms of the electrons. This forms a something like an accumulation layer. This is what we call as hole accumulation layer. On the other way, if we have a little more gate voltage, say greater than 0 but less than threshold voltage, then acceptor atoms were there which accept the electrons and become ionized. So immobile acceptor ions. Okay, that's what it is showing. So Bg is less than Btn, then this happens. And if we have this greater than Btn, then we have a thin electron layer, and there is also this depletion region in which acceptor ions are there is present. Okay, so this is how the action looks like under the gate, which is nothing but the metal oxide semiconductor structure. Okay, so in this MOS structure, this thing happens. One very important thing which can be now at this point discussed here, that as the charge is changing with the application of the gate voltage under this gate. Okay, so is the capacitance also changing in the starting for the Vg less than threshold voltage. When this was very less than threshold voltage, that is Vg is also negative maybe. In that case, it is in accumulation region, and a change in the gate charge also makes a change in the channel charge, corresponding channel charge, and the separation between this channel gate charge and channel charge is quite small. Okay, so we have a large value of capacitance. So in accumulation, you can see, we can see here in accumulation before this we have a large capacitance which is given by COX. So COX actually here the action is quite similar to the parallel plate capacitor, in which two plates, okay, metal plates say, are separated by a dielectric material of permittivity epsilon ox, and let us say that this is having some area A here, these plates. So the capacitance due to this can be written as epsilon ox A upon T ox. T ox is the separation between this, okay, thickness of this oxide, T ox. This is filled by dielectric material of epsilon ox permittivity. So this is absolute capacitance. If we want to represent the capacitance per unit area, then we can divide this above capacitance by the area, and we have epsilon ox upon Tx. In some literatures, this is also written as C dash or C dash O or C dash OX. Different representations are written. So this is COX here, which is, let us say that epsilon OX upon TOX, because of the parallel plate like action in the accumulation. Similarly, when we apply a gate voltage greater than threshold voltage, then there is inversion region, and if the change in the rate of change of this voltage applied is slow in the sense means, so that here what is the action here, okay, let us see. As we apply a gate voltage greater than threshold voltage, the electrons are being attracted, okay, from this substrate, okay. The electrons go and uh, are just being collected at the interface here. Okay, so it will take some time to adjust these electrons to from the substrate to the interface here. So if the gate voltage is slow varying, then in that case these electrons I'm sorry here, anyone is able to understand this what I am discussing? I am very sorry here, just I remember here that I think this is basic electronics course, okay. I am really sorry, okay. I started with the thinking that it is 6 semester course. Anyone is not responding, what is happening here? Someone should have stopped me.